All right, let's get started. Couple quick announcements. So homework number 2 is due today. You all should be turning that in. Homework number 1, I've given that back. The solution is posted on Blackboard. In general, I think everybody did pretty well. I think it was little things, just little mistakes with like tributary widths and whatnot here and there. The solution's posted. It should be pretty clear, like it's 1 page per problem and it's broken down pretty sequentially. I use a particular piece of software to produce the solutions, which is sort of why they look the way they do. But if you have any questions about that, just sort of review it and maybe look it over, and we can talk about it later. Don't forget, before exams, we have our exam review session, so we can always talk about homework assignments then. Again, homework number 2 is due today. I know that one was a little bit of a long one. That was a little bit of a long assignment. Homework number 3 is not. It's pretty short, so I gave you a little bit of a break on that. Homework number 4 is kind of beefy, and then that's homeworks 1 through 4. That's your first exam. So one thing about this class, and I know this is way down the line, but this is not a mistake. Homework number 5 is actually not covered on an exam. Homework number 5 is on T-beams and doubly reinforced beams, and so it's a lot of just more bending stuff. And since the first test is on bending and the second test is on shears and deflections, I decided long ago that I'd give you homework on T-beams and doubly reinforced beams, but I wouldn't give you it wouldn't be on the exam. So give you a little bit of a break. So unless you want me to put it on the exam, I'd be more happy to. Okay. Now, there we go. There we go. Okay, so homework number 3 is due on Wednesday. On Monday, I'll open it up for questions on that. Only other thing I'll mention, on Monday, there's going to be another faculty coming in just doing an observation of the class. So if you see somebody else in here, like, who's that guy? Pay no mind. It's like the Wizard of Oz. Pay no attention to that man in the corner, So, yeah. Everybody good? All right. Let's see. Today's going to be a little bit like movie time, but we might start to get into an example. But it's lecture 11, and we're finally going to talk about design. Okay? I know. It's like, God, Dr. Mike, what's taking you so long? So here's sort of the stage that's been set up until now, and you can see where we're headed moving forward. So we've spent the last few lectures assessing the capacity of a reinforced concrete section, okay? And so the idea behind what we've been doing up until now is we've been saying, okay, here is a beam, how much capacity can it withstand? Like, how much load can it withstand before it's going to fail? And we've been expressing that in terms of a factored bend, or a factored moment, a phi-mn. So we compute a nominal capacity, and then we adjust that through a strength reduction factor phi. Okay, and that's the absolute maximum capacity the beam can withstand, adjusted with resistance factors. Now that we understand that, now we can ask another question. We could say, okay, let's say, for instance, that I have a series of loads on a beam. Okay? What does that beam need to look like in order to safely resist those loads? And so what I mean by that is, how wide does it need to be? How deep does it need to be? How many pieces of rebar need to be configured in what pattern? Okay? And so that's going to be what we look at right now. Now, in order to talk about this intelligently, and in order to gauge our discussion or guide our discussion, I want to talk about 2 things. First thing, I want to talk about economy in reinforced concrete beam design. And in order to do that, I'm going to have to bring up my phi value again. And I'm particularly wanting to emphasize that equation in the transition region. And so you'll see where that comes up here in a second. But I am also going to define a new term. Okay? This term is, it might not seem very important, but from a design perspective, it's actually an incredibly powerful parameter for the purposes of design. We're going to define what's called a reinforcement ratio. Okay, and so that reinforcement ratio is rho. Okay, Now, what is rho? Well, basically, first off, here's the equation. Okay, it's the area of steel divided by BD. Okay, so the upper part of the fraction is the area of steel, and the lower part of the fraction, you can sort of think of that as the area of the concrete. Like, I know the area of the beam is B times H, but really, we don't really care about the height of the beam, the total height, from a resistance standpoint. We care about the effective depth. Okay, so you can sort of think of this as a percentage, like how much steel is in the beam versus how much concrete's in the beam. So one thing I'll tell you right off the bat, rho values, so that little funky looking P is the Greek letter rho. Just so you know, rho values are small, okay? So when you compute them, you're going to get like a 0.0069, whatever. They're going to be small, okay? And that's okay. So I want to tell you that right now. If you're computing a rho value and you get 26.2, you did something wrong, because that is a lot of reinforcement for a beam, okay? They're going to be small, so that's okay. Now, let's talk about rho, okay? So let's look at these upper expressions. These should be pretty familiar by now, right? So what's the very top expression? That's C equals T, right? Remember, the left is 0.85 FC prime AB. That is the total amount of compressive force that you get out of your stress block. And then ASFY, that's the total amount of tensile force that you get out of your steel, right? So compression has to equal tension, and we use that principle in order to solve for A, right? And this is the formula that we used in our previous couple examples. Everybody okay with that? So what I'm going to do is I'm going to basically take this expression for A, and I'm going to introduce this rho term to sort of get rho into the mixture a little bit. So if the area of steel over BD is rho, I can solve for the area of steel right here. And so all I'm doing is taking that and plugging it into A and simplifying a bit. That's just a little bit of alphabet soup, right? Not too bad. Okay? Next, what do we have? Well, we have Mn. How do you compute Mn? Well, you take your force times your moment arm. We use ASFY for the force because we're lazy, right? We'd rather use 2 expressions as opposed to 4, 0.85 FC prime AB or ASFY. I'm a little lazy. Let's use the ASFY. Okay? The A term, we've got the A term here. And so what I'm doing here is I'm taking these expressions for the area of steel and for A, and I'm just sort of plugging them in here and simplifying my algebra, and I get this. What's in that box? Everybody okay with that? Okay, now what's in that box? I'm sure you're like, come on, Doctor, why? Why are you doing this? Like, why are you throwing a bunch of symbols and alphabet soup? Come on. Keep it simple. Well, there's a very specific reason why I'm doing this, okay? Look at that box. That box, inside that box is an equation for the moment capacity of a beam, okay? And it's a function of 3 things. It's a function of the dimensions of the beam, it's a function of the material parameters, and it's a function of the reinforcement ratio, okay? Why is that important? Well, I can divide out this term BD squared, and so I can sort of normalize this and sort of take out, if you will, the parameters related to the beam's dimensions. In other words, this Mn over BD squared is sort of a normalized expression of the beam's capacity where you've sort of taken out the effect of how big the beam is. As for FC prime and Fy, well, we can take default values, like 4 KSI concrete and 60 KSI steel, and so what we get is we get a measure of how does the reinforcement ratio affect how strong the beam is. Now, I don't think that there's any mysteries of the universe in that plot right there. Put more rebar into the beam, it's going to hold up more load. Of course, right? That's easy. That's pretty easy to understand. But that's not the whole picture. Here's the whole picture. I don't care about Mn. I care about phi Mn. Phi Mn is our usable moment capacity. That's our nominal moment capacity adjusted by that resistance factor. Now, what does the resistance factor look like? Well, it changes, right? It changes depending on the strain in the steel. By that very logic, it's also going to change dependent on how much steel you put in the beam, okay? And you get a really interesting trend. So notice how we have sort of three regions for beam capacity, or three regions for our resistance factor. Well, you get three regions for your beam capacity. You get this, this, and this. Everybody see that? This is actually kind of a nifty find. Look what's going on from here to here, okay? I'll even do this on the screen because I think it's kind of important. Look what's going on from here to here. Look at your x-axis. The reinforcement ratio is increasing. But is the capacity increasing? Not really, right? So in that transition region, what happens more often than not is you just start throwing a bunch of rebar into the beam. It doesn't matter. You're not increasing your phi-mn substantially. So what this tells you from a design standpoint, if I'm the designer, I want to keep my design in this region. I want to keep my design in the tension-controlled region, where I'm actually able to use that capacity or able to use as much of it as possible. I mean, I certainly don't want to use the compression-controlled section over here. First off, that would be dangerous. Second off, the code doesn't permit it. But third, it's not very economical. And that's what happens when you throw a boatload of steel into a reinforced concrete beam. It just doesn't do you any good.
So there will be, so when we start putting the steel in there, it's going to start rising for its capabilities of reinforcement.
Mm-hmm.
Eventually it will plateau.
When you get into transition regions, you start upping the steel, you don't get much benefit out of it. You just don't.
But eventually you'll start getting something.
But that's a good question. But keep in mind, over here, this is compression control. And we wouldn't want that anyways. Because remember, when a compression-controlled section behavior is presented, that means that the concrete is going to crush before the steel yields. And so when the beam goes, it's going to go quick. So we don't want that to happen anyways. Yeah. The concrete's going to govern the behavior, and we don't want that. So, everybody else okay with that? This is a good observation. Okay. So, do we agree that in design mode we would prefer beams to be tension controlled? That makes sense, right? It's desirable behavior, and we're getting the most capacity out of our concrete beam, right? You know, in a tension-controlled region, we're only reducing the capacity from here to here, whereas in a transition region, we're reducing from here to here. So we're getting penalized more by using a transition beam as opposed to a tension-controlled beam. So we agree that a tension-controlled beam is where we want to go, right? Now, when you have a tension-controlled beam, what's your phi value? 0.9, right? So in design mode, what do you think would be a reasonable assumption for phi? 0.9. So right off the bat, I think you could probably conceptualize our design method. You know, the first thing that we're going to do, we're going to have a beam. It's going to have a bunch of loads on it. You know, a dead load, live load, span load, or whatever. So the first thing that we're going to have to do is we're going to have to compute the moment, right? You know, WL squared over 8. We're going to have to compute the factored moment, okay? Once we do that, we're going to try and determine how much moment capacity we need out of the beam. And so we're going to divide that by a phi value. Now, we're going to have to make a guess on that phi value because we're in design mode. We don't have a clue what the beam looks like because that's the whole point. We're trying to size the beam. So we have to guess a phi value. And what phi value are we going to guess? 0.9, because that's the value we want. We'll have to go and verify that later, but that's the value that we're going to target for our design. Make sense? Okay. Now, one nice thing about this expression that I derived earlier is that you could take that expression, do a little bit of algebra, you know, rearrange that a bit, and solve for BD squared, and you get that box down below. That's a pretty powerful equation, because look at what's in that box. That box tells us what BD squared is. BD squared is essentially a measure of how big the beam is. So that box is telling us that, you want to know how big the beam is? Here you go. Mn over Fy times what's going on in that series of brackets. And so in design mode, if you're trying to determine how big the beam needs to be, you need 3 sets of parameters. You need the nominal moment capacity, which you can get that by taking your mu and dividing it by an assumed phi value. That's pretty easy. You need an Fy and an Fc prime. You can guess a pretty standard set of values at the beginning of the problem. And the only thing you need is that rho value. So what do you use for rho? Well, rhos, again, they're really important, okay? It's a new term, and I know this is the first time that you're seeing it, but rho values, or reinforcement ratios, if you ever hear me term the reinforcement ratio, they are very, very important because they are essentially the primary tool that we will use to select reinforcement patterns in reinforced concrete beams. Now, in design mode, we need a rho value. And I propose that there's really 2 simple ways of going about it. The first is to use a rho value based on a rho value for design purposes. Okay? And the second is to use a rho value based on a given strain. To be frank, this one based on a given strain value, it's a little more tricky, so I'm going to take my time with that. Let's talk about this first one. Okay? We're using ACI specification, so ACI 318. So your textbook in this class references ACI 318. I don't make you purchase ACI 318 in here like I do in steel design, like I make you purchase the steel manual in steel design, because it's a little different. You only need a few provisions in order to do a lot of concrete design, and a lot of those are in your textbook. Now, if you open up the current edition of ACI right now, you will not find this limit, okay? This used to be in the spec a while back. It was a reinforcement ratio limit that all beams had to meet in order to meet deflection limits. We don't use it anymore. However, it's actually pretty useful in design, okay? This reinforcement ratio, this 0.18 FC prime over Fy, this is a really useful tool that works pretty well to give you an initial reinforcement ratio for the purposes of design. It works pretty well. When I design beams, if I need something, quick and dirty that'll get me a reinforcement ratio really quickly, I'll do this. It's really simple. It works pretty well. If I'd like to be a little more scientific about it, what I can do is this, is I can say, maybe I'd like to be a little more scientific. Maybe I'd like to design my beam so that it has a certain strain in the steel. And I can design it so that I know the strain is 0.005, or I can design it so I know the strain is 0.01, or something like that. Okay? So I can use my similar triangle expression like I had before. I can say 0.003 is to C as whatever this strain value is to this. And I can solve for this ratio of C over D. Why is that important? Well, I can take this expression for A, right? Remember, this is my expression for A, ASFY over 0.85 FC prime B. And I can say, all right, well, I replace that with this new term, using rho. I can say, well, what does that matter? Well, A equals beta 1 times C, so C over D equals that. So I've got this expression for C over D. I got this expression for C over D. I can set the two equal to one another and solve for rho. And so basically, I can use this expression if I'd like to be a little bit more scientific about my design. And I can say, all right, what reinforcement ratio is necessary in order to achieve a target strain in the steel? Okay, so remember, what's the strain limit for phi to be 0.9? Like, what's that magic value? Not 0.004. Remember? No, you're guessing now. What's that? 0.005. Remember, here's our, let me go back a little bit. Here's our curve for phi, right? And remember, at 0.005, anything past that, that's when phi goes to 0.9. So if I want, instead of picking some rho value out of the sky, which would sort of be what's going on here, I can instead say, why don't I pick a rho value to achieve a target strain in the steel? They're both perfectly reasonable options, and I'll show you where they fit into the design method here in a second. But does everybody kind of get an idea of where I can use a rho value, or what rho values I can use? Okay. If you're okay with that, excuse me. If you're okay with that, then let's talk about this. All right? You will like that I've given you this because I've given you a nice, pretty, plug-and-chug set of procedures for the design of a beam. But I think after what I've just talked about, I don't think that this stuff is mystery of the universe complicated. I think it's pretty simple. Now, what I'm going to do here, let me go back. What I'm going to do is this. I'm going to illustrate for you two types of reinforced concrete beam design. The first is designing a beam with an unknown cross-section, okay? And so what I'm talking about there is I have a beam, 20 foot long, got this much dead load, this much live load, and I don't have a clue what this beam looks like. I don't have a clue. I don't know how wide it is. I don't know how deep it is. I don't know the rebar. I don't know anything about it. That would be designing, assuming an unknown cross-section. Have no clue at all what the beam looks like. Designing for a known cross-section, that's a little different. My folks in senior design who've been doing some research on bridge solutions have probably found a lot of precast solutions, right? So what do I mean by precast? Well, a lot of times in concrete land and in reinforced concrete design, a lot of times what we're doing is we're using what are called precast solutions. So you go to a concrete precast plant and there's a series of beam forms and they're churning out reinforced concrete beams all day, every day. They're churning out post-tension segmental boxes and hollow core slabs and ASHTO girders and all of these beams where the shape of the beam has already been figured out. So in that design mode, you know what the beam looks like. You know the shape of the beam. You know the cross-section. What you don't know is the steel. You do not know the reinforcement pattern. Okay? So we're going to go through two different types of design procedures for reinforced concrete beams. One where you don't know what the beam looks like at all, and one where you do. Does that make sense? So in this mode, there are three parameters that ultimately we're trying to figure out. How wide the beam is, how deep the beam is, and how much steel goes in it. For a known cross-section, we only got to figure out one thing. How much steel goes in it. Okay? Both are very relevant design problems for a structural engineer, so we're going to do both of them. Sound good? Now, after I go through this design procedure, I don't think that you're going to see, like this isn't going to seem like mystery of the universe stuff. It's actually going to be pretty straightforward. So let's start off with an unknown cross-section. This one's the harder one. So if you can do this, you can definitely do the known one. So this is where I don't have a clue what the beam looks like. So the first thing I've got to do is I have to determine the factored moments on the beam. Okay? Now here's the thing. What load must all beams be able to withstand? They have to be able to withstand their own self-weight. Well, how much does the beam weigh? I don't have a clue because I'm in design mode. I don't know what the beam looks like. That's the problem. So I have to guess something. I have to assume something. Now, in all honesty, if you all were structural engineers for 10 years and you had thousands of beam designs under your belt, you wouldn't need to do this. You'd be able to look at a beam and go, that beam's going to weigh about 400 pounds per foot. And you'd guess that value, and then when it's all said and done, the beam's probably going to weigh about 400 pounds per foot, okay? Because you just got that experience. Well, you all don't have that experience, okay? You're brand new at this. So what I'm going to do is I'm going to give you a little bit of guidance on how to assume the beam self-weight. Now, in order to do that, we're going to use some ACI requirements on height limits, okay? So, for instance, if you have a beam, it's a simply supported beam, its minimum height, the height of the beam, is the length of the beam divided by 16. And that's the minimum thickness that we use for whether or not we need to consider deflections in our calculations. So we're going to use that. It's sort of an ACI limit for us. We'll use that as a guide for how tall the beam is. As for how wide the beam is, to keep it simple in design mode, we'll say, well, if the height, let's just say it's 20 inches, we'll take the width as 10 inches. We'll just cut it in half. Now, I'm going to be honest, this will result in a beam size that's probably smaller than what we're really going to get. But it's not going to be out there. It's not going to be, so far off that we're going to have to iterate like crazy. But it's at least a good starting point, and it's easy for us to use to get started. And when it's all said and done, you can produce a pretty economical design.
Does that work for units or doesn't matter?
Sorry, what?
It doesn't matter what units are?
Well, no, I mean, that's a good question. So if the span length is 20 feet, what's 20 divided by 16? What, one something what? Like, what are the units?
Oh, yeah.
Feet, yeah. So if you take 20 divided by 16, you're going to get 1 point something feet, or however many inches.
Okay.
Yeah. So just be cognizant of your units, that's for sure. Yes? No, that's fine. That's fine.
We solve for BD squared or BD. I don't even know exactly what B is. B. Just got to multiply together.
Oh, you're exactly right. Oh, we're going to get there. Don't worry. All right. So when it's all said and done, you're going to have some dead loads on the beam. You're going to have some live loads on the beam. Some of those dead loads are going to come from the beam self-weight. And when it's all said and done, you're going to get an MU, a factored bending moment on the beam. On homework number 1, you should have had some experience doing that. Remember, what was the first problem? You had a floor plan, you had a dead load, a live load, you had to reduce that live load, tributary area, distribute it to a floor beam, WL squared over 8. Y'all remember that? So you all should have kind of an idea of how you would get an MU value, right? Well, here's the thing. If phi has to be greater than or equal to MU, so phi mn has to be greater than or equal to MU, how do we get an MN? MN has to be greater than or equal to MU over phi. So our required MN is going to be MU over phi. Well, the problem with that is we don't know what phi is because we don't have any idea what the beam looks like. So we assume something, okay? So one of the things you'll notice in these procedures, see how I've got these bold underlined things? These are all assumptions that we are making throughout the design process. So every one of these assumptions we're going to have to verify at the end, okay? That's just the nature of design, all right? Now, once you've got your MN required, you need a rho value. Now you can use one of two things. You can use this simple formula here, or you can use this little bit more scientific formula here. You'll know in design mode which one you need to use. If I was designing something, on a desert island and didn't have any other resource or anything to go off of, I'd use the simple formula. But if it's on homework, on an exam, I might make you use a little bit more of a scientific one just to make sure that you all are following along. But once you've got an MN, once you got a rho value, we can next compute a BD squared. Okay, now, you asked a very good question. You said, well, if you got BD squared, how do you figure out what the B is and how do you figure out what the D is? Well, typically what we will do is we will choose a B over D ratio or a D over B ratio that is economical and go with that. So what's a good B over D ratio? Typically in most beam design, anything between like 1.5 and 2.5 are pretty good values. So you'll see here in our example that we're going to do, we're using a B or D over B ratio of 1.5. But 1.5 to 2.5 are pretty good. And that comes from just experience. I mean, and you don't have to take my word for it. You could, for instance, take this problem, we're going to use 1.5. Why don't you do it and do it again and say use a D over B ratio of 4. I guarantee you your beam is not going to be as economical as mine. Okay? And that just comes from experience. So anything between like 1.5, 2.5, that's going to be a pretty good range. All right. Yes?
So this is
Yes. You mean like at the yes, yes. Okay, so that's a very good point. Right now, we're just doing rectangular beam design. Okay, a couple things. One, we're going to do T-beam design later, so that's, I mean, how we handle that, that's going to be a little different. Two, if you are doing, let's say you're doing something like wonky, like a AASHTO girder or a post-tension segmental box. And let me pull up like an AASHTO girder so that you all kind of have an idea of what I'm talking about. This I don't want to discard. Let's see. Type 4. Okay, so this would be something like an AASHTO girder right here. So the girders, they have different configurations. Just so you know, these are primarily bridge girders. And you've probably seen beams like this if you've been driving down the highway and looking at bridges. You've probably seen concrete beams that look like this. These are precast and pre-stressed elements that are designed for bridge applications. Now, how do you determine the moment capacity? Well, let's assume for the sake of discussion that we don't have to consider pre-stressed. All it is determining, you know, where's that depth here such that C equals T, and then doing a moment arm. Now, is your stress block a little more funky? Yeah, your stress block's a little more funky, but you all took statics for a reason so that you could determine centroids and moment arms and things like that. So all you'd have to do is say, okay, here's the point where C equals T. Let's determine the centroid of this shape. Let's determine that moment arm and fee them in. So I don't want you to think it's impossible. Like, I'm not going to make y'all do that in here, but I don't want you to think it's something that you can't handle, because you, of course, can. One of the nice things about a lot of these weird, wonky cross-sections is because the geometry is a little weird, a lot of times your moment capacity and things like that are already calculated for you as an engineer. Like, you'll find these design tables, say, oh, AASHTO type 3, here's my concrete, bam, here's MN. Those are lookups if you need. But if it's something really weird, it's just centroids. This is good stuff. I like this. Any other questions? Cool. All right. So where was I? Okay. So we got an MN. We got a rho value. We compute our BD squared. So BD squared is sort of like a measure of how big the beam needs to be. And then we pick B and D values based on our ratio. Now, so what in design mode, we're going to have a width of the beam and we're going to have an effective depth. But we do kind of need to know the height of the beam. Unless otherwise stated, I would take the height of the beam to be the depth plus 3 inches. Okay? The reason why is because 3 inches is a very reasonable value for cover requirements. We're going to talk about cover here in a second. But usually you need a little bit of cover here, and then you've got your stirrups, and you've got your bar size here. 3 inches is usually a very reasonable value for design. So unless otherwise stated, go with a height of D plus 3 inches. And again, I'll talk about cover here in a second. Everybody good? So at this point, you know how wide the beam is, how tall the beam is, and the effective depth. The only thing that you don't know is the area of steel. So you're going to take your area of steel required. You're going to compute rho BD. So rho BD will give you the area of steel. Then what you're going to have to do is you're going to have to choose a reinforcement pattern that makes sense. I'm going to show you that here in a second. Here, actually, let me pull that up. So on Blackboard, you should see this. I'm going to print off copies to bring on Monday. Okay? But what I have here, there ain't nothing special about this. It's just a big Excel file. But what I have here is, okay, let's say I have number 7 bars. Move the mouse. Okay, so if I have a number 7 bar, I know that one of those bars is 0.6 square inches. 2 of those bars is 1.2 and 1.8 and 2.41 and so on and so forth. And so what's going to happen is this. You're going to compute a required area of steel. And let's make up a number. Let's say it's 3.5 square inches. What you're going to do is you're going to start going through each of these iterations and say, well, if it's 3.5 square inches, I could use 6 number 7s. I could use, I could use 5 number 8s. I could use 4 number 9s. Y'all see how I'm doing this? So let's just use these 3. Okay, so let's say this, this, and this. Of these 3, which one would you pick? Why? There you go. Exactly right. It's like the opposite of the Price is Right. You know, the closest without going over, you want to go over, right? It's like the opposite. Anybody watch Price is Right? You could, but I would highly recommend against that. Think about it like this. We're talking about, in this course and in general in reinforced concrete design, I want you to think in the back of your head about the concept of repeatability. Imagine this beam's going to be fabricated 800 times. Do you want to make it complicated or just mix it? Yeah. So I wouldn't do that. Everybody okay with this? Now, there's another side to this design chart, but I'm going to show you that here in a second. Let's go back to the design method. So once you choose a reinforcement pattern, you've got your beam. You know how wide it is? You know how deep it is? You know the steel? Are you done? No, you're not done. You need to analyze that beam and verify that phi mn is greater than or equal to mu. Verify that all those ACI requirements that we discussed earlier have been met. Why? Because we guess things. We guess the phi value. We guessed the initial weight of the beam. So you got to verify it, okay? And so that's sort of your last step. Yes.
Back on the rebar.
Yes.
Do we want to consider the price of the different rebars rather than just the area?
That is an excellent question. So the question was, do you want to consider the price of each rebar and not just the area? That's an excellent question. More often than not, though, steel prices are a sort of a per pound type basis. So a bar that has a bigger area is going to be more expensive because it's heavier. So usually, more often than not, the smaller area is going to cost less. But there's another issue that I think you need to consider. Let's say, and I'm making up some numbers here, but I'm doing this just for the sake of discussion. Let's say that I had 2 reinforcement patterns that had identical amounts of steel, the identical area. One of them was 20 number 3s, and one of them was 2 number 11s. Which one would you go with? Like 20 little bars or 2 big bars? What would you do? If it was, just for the sake of discussion, assume it was the same area. So mathematically it's the same. Why? Yeah, that's right, but I want to hear why. It's less to deal with on the site. So there is something to be said about, you might save some. So the point I'm making is you might save a little bit of money by using more bars, but don't get too crazy with it, because somebody has to build this beam, okay? And so if you can get by with using fewer bars, and it's going to save you, or it's not going to cost too much money from a material standpoint, I'd probably go with it, because while you might spend a little bit more on materials, you're going to save money on labor. So I don't want you to think that's the point I want to make, is that there's not just material, there's labor and there's time that goes into the fabrication of these beams as well. So it's not, don't look at just this one issue, look at the whole thing. For our purposes in the class, we're going to say the smallest AS. That's what we're going to do. But just keep in mind, it's a bigger picture. Yes? Stagger factors. Well, you're onto something. So the short answer is yes, and I'm going to talk about that here in a second, but what do you mean by stagger factors? Not really stagger factors, but there's another issue that you need to consider, and I'm going to talk about that here in a second. Everybody with me so far? The issue that I'm talking about, that I want to mention now, is the issue of cover. Okay? So does anybody know, has anybody ever done any work with concrete or anything? Does anybody know what cover is? What is cover? That is exactly right. It is the amount of concrete outside the rebar. Okay? In other words, if you have a beam like this, you never put the rebar like right on the edge of the beam. You embed it a bit. Why? Like, why is this an inch and a half? Why isn't it 2 inches? Why isn't it 3 inches? Why? Well, it depends. Okay? Cover requirements generally are defined by the environment that the beam will be in. So to give you kind of an idea, why do you think cover for, let's say, bridge piers in Miami, why do you think that cover is something like 4.5 inches? Whereas cover for beams in buildings is only 1.5 inches. What is going on a bridge pier in Miami that's not going on a beam in the inside of a building? Outside and what's something else? The salt water, right? See, steel and salt, they don't really like each other very much. And concrete and salt don't really like each other as well. It's going to cause corrosion. What happens to metal when it corrodes? Well, yeah, but if you take a piece of metal and it corrodes, what does it do? Anybody know? No, it expands. When metal rusts, it expands. Imagine you have a piece of rebar inside a beam and it corrodes. What do you think it's going to do to the beam? Correct. Spalling. Exactly right. You're going to have some problems with the condition of that concrete. And so one of the ways that we get around that is we ensure that proper cover has been used. For instance, here's one for you. If you're looking at a bridge deck, like a typical bridge deck in West Virginia, spoiler alert for you folks in senior design, the cover requirements for the rebar in the deck are different if you're looking at the cover from the rebar to the bottom of the deck versus the cover from the rebar to the top of the deck. For the cover from the bottom, we only require 1 inch of cover, whereas from the top, we require 2.5 inches. What do we put on the top of bridge decks in West Virginia where we would need extensive cover requirements? Road salts, right? So we require more cover because of that, right? Does that make sense? Everybody okay with that? Okay, so that's one issue we have to consider. Another issue we have to consider is this. Let's take a look at this beam. Okay, so I got a beam and I got 3 number 10 bars. You tell me, don't you think those bars have to be some distance away from one another? Right? Did y'all learn this in CE 321? You know, if you're making a batch of concrete and you got so much aggregate size, if you have 3/4 inch aggregate, that'll tell you how far, what's the minimum space between bars so that concrete will get in between that aggregate. I hope y'all talked about that. But does that make sense? Okay, all right. So typically, for concrete that we use, let's say in beam applications, we have a limit on our bar spacing. Like, we can bundle bars like we can actually wrap bars together in some instances. I actually don't recommend it, but you can if you need to. But if you're going to have bars spaced, normally, traditionally, these bars can't be super, super close together because the concrete has to penetrate in between the bars. So we have a limit on the bar spacing, okay? Typically that limit, according to ACI, is the limit of the minimum of the bar diameter and 1 inch, okay? And so all of this is really leaning on the lower part of this table. Okay, let me zoom out a little bit. Okay, what did we say, like what, 6 number 7s? You remember that, 6 number 7s? Okay, I want to scroll down to the bottom. 6 number 7s. Okay, so what this table is on the lower part of that is this is saying the minimum web width, or for our case, if we're looking at a rectangular beam, the minimum beam width for that option. So think about what's going on. Let's say you have 6 number 7s. So you have a beam, right? You have to have an inch or an inch and a half of cover on each end. You've got your stirrups, you've got your 6 bars, and you've got space in between them. So you couldn't fit 6 number 7s in a beam that's only 2 inches wide, right? That doesn't make sense, right? That's a really thin beam. The beam has to have some substantial width in order to fit those bars in, right? And so this is, I think, kind of what you were talking about. If you were to use 6 number 7s in a single layer, I propose that the minimum beam width is about 14.6 inches, okay? So what you're going to do in beam design mode is you're going to pick like a family of rebar options. Then you're going to check those rebar options to see whether or not they'll even fit in the beam. Then, once you've determined the ones that are viable, then you choose the one that's the smallest area. Does that make sense? All right, you, then you, then you.
So is this assuming that we put it all on one straight line?
Yes.
Because what's the difference in putting 3 and 3?
So you would use the 3. So this is the number of bars in a single. So if you had 6 bars and you did 3 and 3, then you would go with the 3 because it's all about width. Okay? No, because this is just a width calculation. So it would still be 3 bars in line. The only thing that would change is you would have to have more concrete, or you'd have to have more depth. So your beam would probably get deeper, so it would probably get a little heavier. Does that make sense? Does that make sense to everybody else? Because if you have the bar, like, remember how when we size the beam, we assume that the height is the depth plus 3 inches. But that's assuming 1 layer of bars. If you had 2 bar layers or 3 bar layers, you'd probably need more height. Does that make sense? Does everybody else?
So that was going to be my question, is the height. So what do you do if you add more?
What I would probably do in design mode is, in design mode, if I just needed a rough value, I'd probably I'd add like maybe another 1.5 inches or 2 inches, for every other layer. But then what I would do is when it was all said and done is I would look at my rebar pattern and I would see if I could squunch the bars up and maybe cut a little bit of weight, but I would do that at the very, very end. Oh, I did? Okay. Are there any other questions? Okay, here's what we're going to do next time, okay? So next time, we are going to do a beam design problem start to finish. I have a 22-foot long simply supported beam. I have 1 kip per foot in dead load. Now that's in addition to the beam self-weight. So there's the self-weight of the beam, and then there's an extra 1,000 pounds per foot of dead load. Then we have a 2 kip per foot live load, and that live load has already gone through live load reduction, so we don't have to worry about that. We're going to use 4 KSI concrete, 60 KSI steel, normal, regular, everyday weight concrete, and a D over B ratio of 1.5, and we are going to design this beam start to finish on Monday, okay? We'll actually do some reinforced concrete design. Sound good? If you are not in steel design, have a wonderful weekend. I think everybody's in steel design, though. So we'll see you in a few minutes.